laptop. So I'm recording now. Last time I recorded like on my laptop, and for some reason it only recorded half. Zero clue why. I did not stop recording. it didn't stop recording like when I paused. It just stopped recording somewhere in the middle. Anyways, so yeah. Again, first part, some combinatorics questions. Well, one combinatorics question from the slides, and then a bunch of graph theory from random places. That's kind of our plan here. I am gonna be kind of monitoring the cat as anyways. And yeah, okay. So if at any point you wanna say anything, you can always unmute. Hopefully I will be able to hear you. I think I will be able to. I should be able to. And of course you can also type something in the chat anytime for me to clarify. Otherwise, I won't ask too many times for the call and response. I'm realizing that this window is not. You can't see the whole thing, so let me fix that. There. I'm just gonna do it like that because I want to make sure you can see the whole page. Yeah. Anyways, so I won't ask a million times, for call and response here, but because we just have a lot of things to get through. But please don't hesitate to send a message in the chat or unmute or whatever. Okay, enough talking. We can get started on a question. Well, I guess, okay, maybe a little bit more talking. Yes, I am recording. I can't type. Recording. It will be posted on my YouTube channel, which is just my name. And I will also post a PDF. PDF will be posted. I took this course a long time ago. You can find my notes at www.tutor.ca/notes. Did not take this course with the same professor, so it is quite a bit different. But anyways, there are notes there. Might not be helpful, but there's maybe notes for other courses that might be helpful. So yeah. I was in engineering. I did computer engineering, so there's a lot of computer engineering related things there. Okay. Well, again, unless somebody stops me, I'm gonna start doing questions, and I won't stop. Oh, we will take a break though, so I will stop. I will take a break though at 7 o'clock. We'll take a 10-minute break, and yeah, okay. So I will start now. So the first question we're doing, I'm gonna refrain from copying and pasting things from the slides. Just I don't seem to be not allowed to have the slides. So for the record, I'm coming up with these questions, out of my brain. They just happen to be similar to the slides. We roll 4 20-sided dice. And then the questions are, similarly a bunch of times, right? In how many ways can we obtain a sum of 10? In how many ways? So part B. How about I do it like this, right? In how many ways can we obtain a sum of A 10, B 20, C 30? And what the heck? We can talk about D 40 or something. I don't know, whatever. Just to extend it a little bit. So this is a combinatorics problem, and remember, combinatorics is all about just like counting the size of sets, right? So we might think about the set of all results. So set of all, maybe 4 numbers from 1 to 20 that can result in that add to 10, or that add to 20, that add to 30, that add to 40, where you can imagine the set, and we want to just basically find the cardinality of the set. So that's what combinatorics is all about. So the point of this question, and the point that, the thing that we're going to use, is that this is essentially, in our analysis of this is like a linear Diophantine equation. So what I mean by that is I'm going to say, let xi be the result of the, the ith, die. So for part A, let's analyze part A a little bit here, right? We know essentially that we're looking for all the values of x1, x2, x3, x4, right? I is some number there's 4 die, right? 4 dice. Where they want to add to 10. Right? And we basically just want to find how many solutions to this linear Diophantine equation. And to be clear, right, we have to note here that all of the xi's, right, are some number from 1 to 20. For all I. Right? So this is an important point. Maybe I'll even put that above this. Kind of fits above there. There. We have 4 dice. Each dice is a d20. We want to add them all to add to 10. How many solutions? Well, this is the point is that we have a theorem for this, right? And to be clear, right, we're looking for all the, non-negative solutions that we have to this. Because every non-negative solution we have corresponds to a certain position of the dice. So for example, right, if we roll I don't know, these are the dice. So if we roll they're d20s, right, but whatever. If we roll like a 5, a 2, a 2, and a 1, right? Then this corresponds to the solution in this Diophantine equation of 5 plus 2 plus 2 plus 1 is 10. Right? So that's one possible solution. So that means if we think about the set of all, rolls of, 4 d20s, that sum to 10, and we think about the set, same set, of all positive solutions to star, these two sets are not equal, right? I mean, kind of, right? So here we have like 4 numbers. Here we have like x1 equals, x2 equals, x3 equals. They're pretty much the same, right? We'd say that they are, isomorphic, or there's a bijection between them or something along these lines, right? So there is they are isomorphic. At the very least, they're isomorphic, right? Like we can say that there is definitely the same. Each one of these corresponds to one of these, and each one of these corresponds to one of these. Okay, so enough talking about that. So now how do we actually find, so like this is what we're trying to find, right? But I'm saying that it's actually the same number of solutions as we have here, okay? Right? And it is important because every solution, well, okay, we'll see when we get to the 30 case, right? So it's not always this simple, but in this case, it is this simple. So, so how many elements do we have in here? How many elements? And remember, each element is like a quadruple of numbers, right? So like 5, 2, 2, 1 is an example of a possible solution to that equation. Well, that's the whole point of the theorem that we also have, right? Which is that the, theorem, the number of positive solutions to x1 plus x2 plus ... plus xn equals r. So the number is r minus 1 choose n minus 1, which is equal to r minus 1 choose r minus n. So whatever, either of these forms work. And so that is our theorem, that kind of tells us how to count these things. And that comes from this bijection, and we can count in this way, right? And it's just a theorem to have in the back of your mind. So, well, that helps us, right? So we have that n equals 4, right? R equals 10. And so this number, right? So how many elements, let me say n denote this. Then we have that n is however you want to do it, right? We could say 10 minus 1 choose 4 minus 1. And then however you're supposed to do that. I don't know. Are you allowed a calculator on this test? I'm not so sure. It's 84. I'm not sure if you're allowed a calculator, but if not, then there's a formula for combinations, right? But yeah. So there's 84, right? Different solutions to this, strictly positive solutions to this, where are we? This LDE. And we know that every solution to this corresponds to one combination of dice rolls that add to, of D20s, that add to 10. So we know that there must be 84 solutions. The answer to this question must be 84. So the answer to that one must be 84. And it's important that these two sets are the same size, right? So we do have to somehow consider that, and they are. And so, okay, so then for part B, I mean, it's more of the same, right? So for part B, I mean, for part B, we still have that, you know, x1 plus x2 plus x3 plus x4 have to add to 20. Same parameters. X1 has to be between 1 and 20, right? And x2, I mean, all the xi's have to be between 1 and 20. Worst case scenario, one of the xi's is 20, and the rest of them are 0. But that's fine still, right? Because we could have that. And certainly none of these could be bigger than 20, right? So let's say x2 is bigger than 20, then there's no way these would add to 20 because they're all strictly positive, right? So actually even none of them could be 20, because if one of them was 20, then the rest would have to be 0 and still wouldn't count. So the largest technically any one here would be 17, I guess, right? Because it'd be 17 plus 1 plus 1 plus 1. My point is mostly just that is all within the bounds of what a dice does, right? What a die does, right? So anyway, so for this one, it's a similar thing, right? So we have this, it's like n is 4, and this time r is 20. I mean, there's not much else to say. It's the exact same logic, so I'm not gonna run through it again, but it's gonna be like, 20 minus 1, choose 4 minus 1, and whatever that is, 969. Okay, the interesting thing comes in the next part, right? The next part. So for part C, this is when we have x1 plus x2 plus x3 plus x4 equals 30. And now we have a detail here. So the detail is that if I consider the set of all the rolls of 4 D20s that add to 30, and I consider the set of solutions to star, and that's star right there, these sets are not isomorphic. These sets are not isomorphic. They do not have the same size. It's not true that every element here corresponds to an element here. Well, okay, well that is true. But every element here does not correspond to an element here. Let's see. Hopefully we can do a little interaction here with the chat, right? So, like, can you think of a solution to this LDE, right? That is not in this set. So this set is strictly bigger. Can we think of an element of this set that is not in this set? Let's see if you. Sure. Yeah. Right. So someone in the chat said, so we could have the solutions 1, 1, 1, 27. This is a solution to the LDE, 1 plus 1 plus 1, 3 plus 27, 30. Great. But I cannot have that as a dice roll, right? It's not possible because they're D20s, right? So I can roll a 1, I can roll a 1, I can roll a 1, but I can't roll a 27. So this set is strictly bigger. Okay, this set, I don't know, strictly, well, how about strictly bigger? Let's just say that, right? Now, someone said in the chat, I think 20 is still in because you can get 20. Yeah, you can still roll a 20, right? Yeah, so, but we can't roll anything bigger. So there are solutions that don't count. So, well, okay, how do we deal with this then? Well, it is still true that this set is isomorphic to a subset of it, right? There are some solutions that correspond to rolls of the D20. So we just want to knock out everything else. And it's actually not too hard to quantify what everything else is. It's just solutions where at least one of them is, at least one of the numbers in your solution, element here, have values greater than 20. So, you know, a valid solution would be like 5, 5, 5. Is that valid? Yeah, and then 15, right? Yeah, there you go. Right? Yeah, that is 30. 5 plus 5 plus 5 is 15, plus 15 is 30, yes. And that would be fine, right? So that set in there, this little smaller set, that is isomorphic to that set. Like, there exists a bijection between them. And so what we can do is we can find the total number of elements in this set, which is not hard, right? Which is going to be what I mean, n equals 4, r equals 30, so it's going to be 30 minus 1, choose 4 minus 1 according to our theorem, which 30 minus 1, choose 4 minus 1 is 3,654. So that entire set has 3,654 solutions. But that's including things like 11127. No good. We want to subtract those, right? We want to subtract those. So now we want to take, you know, count how many solutions have one variable strictly greater than 20. We don't have to think about the case where there's two variables strictly greater than 20, because that's not possible. If I had two of these variables strictly greater than 20, then the sum would be strictly greater than 40, right? But if I just have one of these variables strictly greater than 20, then the sum must be strictly greater than 20, and that's fine. It must be 30 exactly, so we're good. So there can only be one variable, right? So, you know, basically, we're going to say, okay, suppose x1 is strictly greater than 20. That's our first solution, right? And so what I can say is that x1 must be equal to some y1 plus 20, where y1 is just some integer, right? y1 is some, well, you know, is in 1 dot dot dot, you know, so the natural numbers, I guess, right? Sorry. I'll say n minus 0 just to be super clear, right? Right, so just hopefully this makes sense, right? We're saying, well, let's say x1 is the one that's bigger. I don't know. We can deal with it after if it's not x1, right? But let's just say x1 is the one that's bigger. Well, then x1 must be, it's strictly bigger, so it must be some y1 plus 20. Where y1, I can kind of understand what y1 is. Well, it's just some natural number. x1 is still an integer. It's just strictly bigger than 20. So our linear Diophantine equation is going to turn into, it used to be x1 plus x2 plus x3 plus x4 equals, was it 30, right? But now we're going to say y1 plus 20 plus x2 plus x3 plus x4 equals 30. And so we get y1 plus x2 plus x3 plus x4 equals 10, right? Just moving it over. And we know that this equation here has exactly 84 solutions, right? This has 84 solutions as per, you know, part A. So we know that there's, out of these 3,654, there's at least 84 of them that don't count. There's 84 of them where, well, there's one of the variables that's too big. Well, I just said suppose x1 is the one that's too big, but it could have been any of them. And so the logic would be the exact same every time. So there's 84 that have x1 too big, there's 84 that have x2 too big, and only x2 too big. There's 84 that have x3 too big, and only x3 too big. And there's 84 that have x4 too big, and only x4 too big. Remember, there's never a case where we have two of them that are too big, right? It's never the case. Okay, so, well, okay, there you go. So that means that our final answer to part C is that there's going to be the 3,654 minus 84 when the first one's too big, minus 84 when the next one's too big, minus 84 when the third one's too big, and minus 84 when the last one's too big. And so our answer is 3,318. So hopefully that makes sense. That's the logic there. Hopefully it makes sense to see this kind of drawn a little bit better. I don't know about better, but I understand the last part. But how did you come up with y x1 equals y1 plus 20? Yeah, well, it's just another way to characterize this. Like I get what you're saying totally, right? So it's just another way to characterize this. If I have x1, a natural number, there's a couple of more things I know here, right? So I know x1's a positive natural number, strictly bigger than 20. Well, that must mean that it's 20 plus something, right? Plus something that's not 0. Plus some natural number that's not 0. Oh, well, there you go. So that must be why. That's why x1 is equal to y1 plus 20. Okay, good. Can you explain why 84 is subtracted multiple times? I missed it. Yeah. So we have that this set, right, has size 3,654, but there's many solutions which have one of the dice rolls too big. So we calculated here that there's exactly 84 solutions to this LDE that have x1 too big. And so by symmetry, because it's the same thing again, there must be 84 that have x2 too big, and there must be 84 that have x3 too big, and there must be 84 that have x4 too big. So I just subtract that 4 times, one for each of them. And so we get that number at the end there. Okay, I think we should move on. I want to keep moving here. So I know I said 40 there, but maybe let's move on to the graph stuff, because that took a little bit of time. But hopefully a good explanation of everything. Yeah, so please feel free to ask more questions if you have any questions about this stuff. Otherwise, I'm just gonna keep moving. But again, this is recorded, and it is recorded, and the notes will be posted and all that, right? So you can take a look. Okay, so next I have a textbook question for you guys. Talked about the pigeonhole principle, right? You had the pigeonhole principle at some point in this course. Hopefully, no pigeonhole principle. Oh, it won't be covered. It got skipped. Oh, okay. Okay, then we don't have to talk about it. There's just like in graph theory, there's a lot of nice times when the pigeonhole principle is used, but if it's skipped, then of course we don't have to. Okay, so now we're going to enter the section of this tutorial where we're talking about graph theory. And so graph theory is a huge field. I mean, you guys had 2 lectures on it, and I looked at those lecture notes, and it's like a crash course. It's like so many things. This course goes really fast, and you guys cover a lot of stuff, which is good, but that has to be backed up with hopefully not too hard examinations. Graph theory is very fun. I highly encourage everybody to study it, especially in computer engineering and things like this, but just in general. And so we're just going to be talking about some of the basic facts. Now, I'm not going to go into like what is a graph and things like this, because the slides go pretty in depth. So hopefully you understand what a graph is. It's a discrete structure, right, that has nodes and edges, and we connect the nodes and edges, and we can have different styles of graphs, right? So we could have an unweighted, undirected graph. This would be called K3 right here. We can have a directed graph, right? So we could have a directed graph like this, where the edges represent directed edge, like the edges are directed, and this could represent information flow through a system and things like this. And then we can also have weighted graphs, right? So this would be maybe cities and the distance between the cities. So we could have this, right? I don't know. And each road has like a certain distance on it or something like this, right? 10, 5, and this one is -2. I don't know. Can't really interpret it as distance anymore if you put that -2, but whatever. I also want to remind everybody that and this is how I like to phrase it. Hopefully I can just find a discrete graph. Is it going to be here? Yeah, I'll just like use this, I guess. Graphs are squishy. Okay, that's how I like to say it. Right. So you can. This is all the same graph. None of these are not different graphs. This is all the same graph. Graphs are about the topological structure, right? So you have like what's connected to what's near what. That's all we really care about. Near meaning like connected to. That's all we really care about. So again, these are all the same graph. That's just an important thing to note here. When I move graphs around like this, it's not different. We would technically say, and it actually says it in your slides a little bit, that we would say these are all part of the same isomorphism class. So these are all isomorphic together to each other. Whereas like here, I mean, this graph certainly looks different than this graph, but I can kind of correspond between the two, that they must be the same graph at the end of the day. So hopefully that makes sense. Maybe we can talk a little bit more about that when we get to graph isomorphisms, which we will talk about. But yeah. Sorry. I am a little bit sick. That's why I'm coughing. So my apologies. Probably not too nice to hear coughs, so cough away. Okay, so I'll start with just a basic fact that we're going to prove about. What am I trying to say? Prove about graphs. And it's not too hard, so just to kind of test the waters a little bit. This is from the textbook. So it says, recall Kn denotes a complete graph on n vertices. Sorry, it's so blurry. I don't know why it's so blurry, but Kn, you can still read it. Complete graph on n vertices. That's Kn. So let's draw K6, and then this is the actual thing that we want to show, right? So we'll just kind of draw it. So K1, that's K1. Okay, there's nothing else to say. That's my favorite way to describe a single node on its own. It's K1. Okay. And then K2 is going to look like this. And then K3 I already drew up there. Okay, and now let's think about how we can construct K4, and this is going to help us with the next one. So K4 is, we have 4 nodes, and they're all connected to each other. One way I can phrase this is I take K3, there's K3, and then I add a new node which is connected to all of them. And then we get K4 from that. And then similarly, that's how we can construct K5, right? So I start with K4. So there's K4. Kind of sloppy drawing, sorry, but and then I take the 5th node and I connect it to everything. And remember, it's isomorphic to if I kind of squish it a little bit and I get it to be in the form that you're usually used to seeing, like a pentagram, right? You see it like that. Okay, and you can imagine what K6 is. But the point really that I want to get at here is like to construct the next Kn plus 1, we can construct Kn plus 1 by taking Kn and adding a new node and connecting it. And how many new edges would we add? Well, we'd add n new edges, right? So how could we show this? Show that for all integers n greater than or equal to 1, the number of edges of Kn is n times n minus 1 over 2. So does anybody have a suggestion of what proof technique we can use for this? I want to prove this, right? So proof. What proof technique could we use here to prove this fact? We have lots of different proof techniques. We have direct, we have contrapositive, we have contradiction, we have induction, we have strong induction. Okay, I got one induction, right? And hopefully that makes sense why it's induction, because I was describing it to you in an inductive way, right? I was saying that we can get K5 by looking at K4 and adding a node, right? So, right. So let's consider, K1, right? So K1 is just a node. And the number of the magnitude of the edge set of K1, which is like the number of edges in it, right, is 0, right? And in fact, we're asking, is this equal to 0 times 0 minus 1 over 2? Well, that's 0, so yes, it is, right? So it works for K1. It's like our base case. Okay, so then our hypothesis, inductive hypothesis, right? Suppose K, however you want to say it, let's say Kn has n times n minus 1 over 2 edges. Show, maybe I'll do it in a different color. Show Kn plus 1 has n plus 1, n plus 1 minus 1 over 2 edges. Right? That's kind of what we need to show. Well, based on our discussion up there, right, we can say that the number of edges in kn plus 1 is going to be equal to what? Okay, so we have kn like this, right? So let's say I have n, this you know, dot, dot, dot. So we have n nodes altogether, 1, 2, 3, up to n, and this is kn, and they're all connected to each other, okay? Then when I construct kn plus 1, I'm adding a new node, and I'm adding dot, 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 n new edges. So hopefully it makes sense that the number of edges in kn plus 1 is going to be the number of edges in kn plus n. We know how many edges are in kn, right? That's n times n minus 1 over 2. That's by the inductive hypothesis, right? So this is, maybe I'll use a green arrow. We can say by star, and that's star. Yeah, could I explain the equals n part? The equals n part? Which one's the equals n part? Like the plus n part? Oh, this plus n, yeah. Right, so we're thinking about how we can construct kn plus 1. One way we can make kn plus 1 is by taking kn, and kn will have number of edges in kn. That's how many edges it will have. Not very insightful. But what we can do is we can add a new node that's connected to all of them. That's what I did here, right? So to construct k4, I took k3, which is in blue, added a new node that adds n edges. N was 3. So the number of edges in k4 is the number of edges in k3 plus 3. So the number of edges in kn plus 1 is the number of edges in kn plus n. And then, you know, whatever. Some algebra, dot, 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 and then this turns into exactly what we want, right? This will turn into, well, okay, so this, to be clear, this is just n times n plus 1 over 2. I don't know, well, that shouldn't be hard, right? No, I think it's going to be, we can do the algebra. So it's going to be n times n minus 1 over 2 plus, we can just, you know, it's 2n plus 2n here. And then what can we do? We can factor an n out. So we have n minus 1 plus 2 over 2. So we have n plus 1 over 2, which is exactly what we wanted, right? And n plus 1 over 2. So I'll leave that on the screen. That's the complete proof. This fact that we got right here, this like pink star, right? That is just from our analysis. Like that's just from our looking at how we could construct kn plus 1 from kn, and you might want to, I don't know, you could prove that, I guess. But it's kind of a recurrence between the number of edges. Hopefully it's clear, though, that it's true. And so, well, then it's pretty simple to prove. You know, in a way, it's kind of like what I've done here is I've kind of, you know, this question is completely isomorphic to here's a sequence, a n plus 1 equals a n plus n, starting with a0 equals 0. You know, find an explicit formula for an, and this would be the exact same question. Very different seeming, right? But it would be the exact same question. Yeah, okay. Anyways, so that's that. If anybody wants to stop me, feel free. Otherwise, I'm going to keep going. So I thought this was a good thing to start with, even though it might be simple. I don't know. What's the impression? Is this simple or is this complicated? Or because I don't want to do things that are too simple, but I also don't want to, you know, I want it to be a helpful tutorial. So I want to do things that are relevant and that people can follow. So what's the impression? Is this too easy or fine or? Okay, a bit simple. It's in the middle. Okay. I thought I was aiming for this one to be an in the middle question. That's why I started with it, right? Okay, and yeah, I don't know if we're going to do that many harder proofs necessarily, but we will kind of talk about, well, I mean, maybe a little bit, but we'll see what we get to. Okay, so I'm not going to solve this question. I was just kind of noting something that's isomorphic, right? So the next one that we're going to kind of talk about, so next example, is basically just this, okay, so first of all, we have the handshaking lemma, right? So the handshaking lemma, let me zoom in a little bit here. So the handshaking lemma says that for any graph G, we have that the sum of all the degrees of the vertices is equal to 2 times the number of edges, right? So for some, G is equal to some vertex set and edge set, right? Then for all V in V, we take the degree, we add it all up, and it's twice the number of edges. It's like the handshaking lemma. It's like the first theorem of graph theory, whatever. So, I mean, it's very, very trivial, essentially. So then we can prove other things from this, and this is kind of the more helpful one, which, I don't know. The number of odd degree vertices of any graph is even. Okay, so that's our, maybe not an example, but that's maybe our theorem. Right. So maybe here's an example, right? So, I mean, let's just draw up any graph, right? I don't know, path or cycle, I guess. Let's do that. So let's find the degree of all the vertices here. So the degree is 2, the degree is 3, the degree is 2, the degree is 3, the degree is 2. And how about, why don't I add one more thing like this? So we get that this is 3 and this is 1. So let's think about the number of odd degree vertices. So we have an odd degree vertex, an odd degree vertex, an odd degree vertex, an odd degree vertex, and the number of them, right, is 4, which is an even number. So number of odd degree vertices equals 4. Odd degree vertices, well, I'll just say odd degree vertices, and that's an even number. So that's all we're saying here. And hopefully it makes sense, because if I try to make another one, like let's say, oh, I'm going to be mischievous and I'm going to add another one here, that's going to screw it all up, because I'm adding just a single odd degree. So maybe it's going to screw it up. So now this is going to be 3, but that's also odd degree. And if I tried to make this not odd degree by maybe connecting it to another odd degree node, well, that would become even. So we'd be losing 2, right? Which is still an even number. An even number minus 2 is still an even number. Or if I connect it to an even degree node, then I'm kind of just switching roles, right? Now this is going to be even, sure, but now that's going to be odd. So hopefully that makes sense, that we can't escape it. And it's very simple to prove. It's basically just from this fact here. So we'll prove it. The standard way is by contradiction, which is the same thing as what's in your slide. So we'll just do that. So again, yeah, someone asking if I could say that again, right? So I'm basically saying that, like, I have a graph here that satisfies the requirements. Excuse me. I have a graph here that satisfies the requirements. And well, I'm saying that if I were to try to make the number of odd degree vertices odd, I mean, there's no way I can do it combinatorially or topologically or however you want to say it, right? Like if I connect, I want to make this node have odd degree, increasing the number of odd degree vertices by 1, so it would be odd. But by doing that, I'm adding another odd degree vertex. 1 is odd, so I still have an even number, right? These would now both count as purple or orange. I don't know, I'm saying purple. So that didn't work. And if I then say, okay, well, darn it, I didn't really do what I'm trying to do. So maybe if I can make this even degree by connecting it to something else, well, if I connect it to an even degree node, then sure, this is now an even degree node, but now the thing that I connected it to is an odd degree node. So I didn't really help myself here. And if instead I take one of my odd degree nodes, whatever this, let's say this, and I connect it to also an odd degree node, then we lost 2, right? We lost 2. So that's 2 and that's 4. We lost 2 odd degree nodes. An even number minus 2 is still an even number. So we really can't escape it. And to be honest, like that's kind of a proof, what I just said right there. Like that would be like a direct proof, what I just said out loud right there. I mean, but like formalize it a little bit. But it's like basically like select a node. Like directly you would say like select an arbitrary node in the graph. If it is either of even or odd degree. So you split into 2 cases. If it's odd degree and you try to connect it to a node of odd degree or even degree. So there's another 2 cases. So you have 4 cases. You have 4 cases to deal with. Then not a very pretty proof. In general, we don't like to, in proof writing, to like break things into a million cases. I mean, it's valid. It's totally valid. But as a style factor, kind of, you don't like to break it into a million cases. So we can just do it by contradiction, right? So we can say, suppose the number of odd degree nodes is odd. So, this is our statement. So we're by contradiction, right? Suppose by contradiction. And remember, when you do something by contradiction, the point is like you do it when it's like, it's hard for me to put into words exactly why this is true, but it's not hard for me to put into words that it simply couldn't be any other way. And so that's the point here. Like by contradiction is it's saying, well, it just simply couldn't be any other way. There's other cases where you want to use contradiction as well, but that's one case, and that's kind of what we're saying here. Okay, so well, then what I can do is I can think about all, the sum of the degrees, so the sum over all the vertices in V, the degree of V. And we know that from our handshaking lemma that this is going to be 2 times the number of edges, whatever, this is going to be even, right? Like that sum has to be even because it's double the number of edges. So it must be even, an even number. So maybe the arrow points here, but really then that implies that that's also even. Okay, so now we're going to find a contradiction to this by saying that, okay, well, actually, we could decompose this. We could imagine splitting our vertex set. We're just adding. Adding is associative, right? Or associative, but also commutative, right? So we can split this into 2 sums. We can think about the sum of all the vertices in V that are, the degree of V is odd. And so we can add the degrees of V. And we can add this to the sum V in V. The degree of V is even. And then we're adding the degree of V. I can do this, right? Because every vertex either has an even or odd degree. So I'm still, this equal sign is true. There's no contradiction there or anything like that, right? That equal sign is correct because every vertex degree is either even or odd. So I'm counting all of them here. I'm just splitting them just commutative and associative, right? So I can kind of just put them together, or actually not put them together, separate them. And we're going to prove that this right-hand side must be odd. So first of all, we have, in this case, a bunch of even numbers being added together, right? This is going to look like even plus even plus even plus dot 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 plus even. So that must mean that this entire thing must be even. Doesn't really matter how many there are. If I'm just adding a bunch of even numbers together, then the result will be even. So that's even. If this is also even, then the whole right-hand side will be even. But if this is odd, then the whole right-hand side will be odd, right? If I can prove that this sum right here is odd, must be an odd number as a result. Then odd plus even, 2k plus 2m plus 1 or something like that is an odd number, right? So okay, well that is what's going to happen. So let's think about what's happening here. All right, we're going to have odd plus dot 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 plus odd. But what actually matters here is that we have an odd number of them. How do I know that? That is what I'm supposing by contradiction here. The number of odd degree nodes is odd. Odd number of them. So we have an odd number of odd numbers. An odd amount of odd numbers being added together. Okay, let's just think about it for a second, right? So if I have 3 plus 5, this is 8. So odd plus odd is even, but odd plus odd, plus odd is 9, is also odd. So we can put this as a claim. An odd number of odd numbers. That's not a good way of phrasing it. An odd amount of odd numbers added together will be an odd number. Numbers will sum to an odd number. And so we can conclude, therefore, that term must be odd. Therefore, this entire side must be odd. And the contradiction comes from the fact that we have an even number equals an odd number. And we're done by contradiction, right? So you can put a little thing like that by contradiction, and then you're done the proof. So it would just mess too much with the handshaking lemma, right? So this is an interesting property. I like the handshaking lemma because it's a very simple fact, but it does tell us, graphs are a representation of relationships as a whole, relationships between objects. Wow, that's really general. And it shows us that just by the fact that we're talking about relationships between objects, there's already things we can say about it, right? There's a restriction to the way things can be related by the handshaking lemma and by lots of other properties we have of graphs, all the other facts we can prove about graphs. But I like the handshaking lemma specifically because you can prove it about, it's true for all graphs, simple graphs, all simple graphs. Even loops are allowed and things like that. It still counts. So not just simple graphs, it's true for all graphs. And yeah, I think that's very cool. Okay, guys, it is 7 o'clock, so we'll take a 10-minute break. And then when we come back, we will start talking about random walks and things like this. And then we'll talk about connected components. We can talk about we'll talk about trees and graph isomorphisms, counting the number of walks, random walks. I like that one. I'm going to definitely get to that one. And if we have time to get to graph coloring and planar graphs and things like this, we'll talk about that as well. Okay, so I'll pause. So I'm going to go to my AFK screen. Break back at 7. Oh, that's pretty close. Let's say 7:12. Let me fix it. Okay, guys. So let's take a 10-minute break. If you have any questions, please feel free to say it in the chat. Otherwise, I'll be back at 7:12. Okay, everybody, let's get back to it. hopefully everybody's here. There we go. So we will go and another 50 or so minutes. This is what we're talking about now. Walks, trails, paths, closed walks, circuits, and simple circuits. All different words for a similar thing. So we're all talking about sequences of nodes and edges and things like this, right? Throughout the graph. So you can imagine traversing the graph in a certain way like this. So here's the kind of, here's the rundown of everything. I mean, this table is pretty helpful. This is from the textbook. So we have all these definitions, and it kind of goes down in terms of how restrictive it is. So a walk is totally unrestrictive. You start at a node. So I am recording, and everybody can see my screen hopefully, and you can hear me. I think we're good. Yeah, so just let me know if there's anything. Okay, so the walk is totally unrestrictive. We start somewhere and we can just do whatever we want, right? So we can kind of just move around, right? We can go back to where we started. We can go say in a cycle for a bit. I don't know. We can go backwards. I don't know. This is a walk around the graph like this, right? That's a walk. Okay, so a walk is totally unrestrictive. If we make the one restriction that we can't repeat edges, then we have what's called a trail. Okay. So if we start, I don't know, I'm just randomly starting at V4. We don't have to start at V4, but if I randomly, I can't repeat edges. So maybe I go like that, then I go here. I'm not allowed to go back there. I can maybe go here. I can't go there because I used that edge already. Or did I? I can't remember if I did. Maybe I didn't actually. So anyways, I can't repeat edges. So a slight restriction in that I can't repeat edges. And a path is more restrictive. I can't repeat edges and I can't repeat nodes. So here it's like I can go, here, but I would not be allowed to use this loop, right? Because then I'd be repeating this edge, this node V3. So that's not a path. So I'd have to go like, something like this, right? That's a path, for example. A closed walk is kind of, we're a little bit back to what a walk is. So remember, a walk is the completely unrestricted one. So that's how I kind of try to remember. To be honest, I don't know if I remember all these. If you quiz me, you see me on the street and you say which one's which. I mean, it'll take me a second to remember which one's which. But walk is the most unrestrictive one, and then trail a little bit restrictive in terms of edges is the first thing that we don't allow repetition for, and then a path is completely restrictive. Right? So of course, if the path you can't repeat a vertex, then of course the start and end points cannot be the same. Then a closed walk has the word walk in it, so maybe we're a little bit more, a little less restrictive again, right? And it is correct. Like, so we can repeat edges, we can repeat vertices. We have to start and end at the same point, though, right? We have to start and end at the same point. So I could do whatever I want as long as I go back to where I started. So walk is kind of like do whatever you want. Closed means you got to go back to where you started. So circuits, right, are closed, right? Circuits are closed. So circuit and simple circuit, they're both closed. And we have a slight extra restriction that they can't be these, like, there's no weird degenerate circuits, right? So if I just pick like this F right here, V1, or if I just pick V1, it is a closed walk, just V1. That's all it is, F, V1. It's a closed walk, but it's not a circuit, right? Because I have to have at least one edge in it. So it's like not allowed these degenerate cases. So so circuits, you cannot repeat edges. For simple circuits, simple is kind of like closed, right? They're both they're both closed, right? They both start and end at the same points. For simple, that's the only time you have repeated edges, repeated vertices. The only time you have repeated vertices is if it's at the first and end. That's the simple. And for a circuit, it's other cases you can have that as well. But so basically, a circuit and a trail are fairly similar, right? You can't repeat edges in either of them. You could have repeated vertices. For a circuit, the difference is that you have to start and end at the same place. And you can't allow these degenerate cases. So a trail has these little weird exceptions. So circuits kind of like we're saying like, no, to these weird exceptions. So circuits are pretty useful. Okay, so there's the, what, 6 different ones. Would I say memorize this table? I don't know. But memorize what I said, kind of, right? So this is in terms of like walks are totally unrestrictive, trails are a little bit more restrictive, paths are the most restrictive, closed walks mean you are not very restrictive, but you do have to start and end at the same place. Circuits, you have to start and end at the same place. And there's no edge repetition. So it's kind of like a trail. Circuits are kind of like a trail. And simple circuits are where the only time you have node repetition is when it's the first and last. Okay, so that 20-second audio clip should be memorized, right? Of what I just said. I don't know if it should be memorized. I don't know what you're expected to look on the test, but in terms of just knowing graph theory stuff, to be honest, I should memorize it. I do. Again, I probably would be able to say if you saw me on the street and quizzed me, but it probably would take me a second to remember which one's which. But yeah. Anyways, in the graph below, determine which of the following walks. So they're all walks, to be clear. They're all walks. Everything is a walk, right? A walk is the most unrestrictive thing, but we can be more restrictive, and we can say they're also trails or paths or circuits or simple circuits. So there's no closed walks here, I guess. But okay, so let's take a look at the first one, and we'll just kind of trace it out together. So maybe I'll do it by moving this. So we start at V1, okay, and I'll kind of demonstrate this by moving this guy around, right? So this might be a little bit, okay. So maybe, how should I demonstrate this? I guess I'll draw. So we start here, and then we go edge 1, and then we're at V2, right? And then maybe I'll call that 3 or something. And then we take edge 3, it's the 4th step. And then we are at V4, which is the 5th step. And then we take edge 4, which is the 6th step. And the 7th step, we're still at V3, right? And then we take edge 5, which is the 8th step. And then we're at V4, which is the 9th step. Okay. So what is a feature of this walk? Well, one important point here is that I repeat V3. So we have a repeated vertex. So it's definitely not a path, right? Now, so it is a walk, of course. So we're not really talking about walks, but so is it a trail? Well, does it have a repeated edge? It does not have a repeated edge. Does it have a repeated vertex? Yes, but that's okay. Does it start and end at the same point? No, but you don't really have to for a trail. And does it contain at least one edge? Well, it does, but so anyway. So it is a trail, right? So this is a trail. It might be other things too, though, right? But it's definitely not a path, right? Because it has a repeated vertex. And it can't be any of the last 3 because it doesn't start and end at the same point. So it's just a trail. Hopefully that makes sense. So that's A. We don't have to do all of them, but maybe I'll just do a couple interesting ones. So I'll erase this again. Then the next one is, okay, B. It's just a sequence of edges. And when it's not ambiguous, you can do this, right? So if we're at E1, right, and then we're taking E3, so I must be starting here, right? So I must be starting there, taking E1, right? That's my second one. Then I'm at this node. Then I'm taking E3, my 4th. I'm here, 5. Then I'm taking I did E3, so I'm taking E5 now. It's my 6th move, and I'm at V4, which is my 7th move. And then I'm taking E5 again. It's my 8th move. And now I'm back here at V3, so it's my 9th point. And then I'm taking E6, it's my 10th move, and my 11th step is there. So when we, pass it to the chat, could this be a path? I see a no, right? It could not be. Why? So it has a repeated edge, and it has a repeated vertex, right? We repeat V3 as well. So it's definitely not a path. Is it a trail? Yes or no? Yes or no, and why? Well, people said repeated edge in the chat already, right? Which is what trails are not allowed to have, and so we definitely not a trail. And it can't be any of the last three because it's not closed. It doesn't start and end at the same place. So it's just a walk. So it can't be a closed walk. It can't be a circuit. It can't be a simple circuit because it's not closed. It doesn't start and end at the same place. Okay, why don't we do maybe we just do C and F. I mean, F is pretty easy, right? So F, we can just talk about F quickly. Why don't we just do F? I think that's probably enough examples of this. So F is just V1. So it's a walk. Is it closed? Is it closed? So does it start and end at the same place? It does. It starts and ends at V1. It's only V1. So it does start and end at V1. So that means that it is one of, well, technically it's just not a path, because it could still be a walk or a trail, but it could be one of these because it's allowed based on that information. We just knocked out that it can't be a path. And it's a little bit of a weird degenerate case, right? But it's okay. But it does not contain any edges. So it can't be these last two. Circuits get rid of these degenerate cases. When I say a circuit, I don't mean something like this, right? I just mean nice, well-behaved path or sequences like this, right? Okay, so then is it a walk? Well, yes, it's a walk. Is it a trail? Well, does it have a repeated edge? No. Does it have a repeated vertex? Technically, yes, but it's allowed. Does it start and end at the same point? Yes, but it's allowed. It doesn't have to at least contain at least one, so it is a trail. It's also a walk, of course. Is it a closed walk? Well, we're allowed to have repeated vertex. Yeah, I that's a little. So someone asked, is V1 technically being repeated here? Yeah, this is a little bit. It's like a degenerate case, right? So it's like a little bit pushes on the definitions of these things, but I would say that it would fall under. It would not be a valid path. Well, would it be a valid path? I guess. Yeah, I don't think it would be a valid path because, well, just a path of length 1. No, I don't think it would be a valid path. I don't think you could call this a valid path. I think because when we talk about paths in other contexts, we sometimes started at 2. We just say that the smallest path is of length 2, right? So I don't think we would call this a path. So it is a walk, it is a trail, and it is also a closed walk. Passes all those conditions too. But it can't be the last two. So someone said, can this be a simple circuit? It can't be a simple circuit because a simple circuit requires you have at least one edge, and that can't be true. I mean, and that is not true for this particular sequence. Okay. With that, I will move on to the next part, unless someone has a question. So I'll maybe erase all the drawing on this, right? Just to... Yeah, we don't have to do all of them here, but... Okay, so the next thing that we're going to talk about are components. Components of G. So when I draw a graph, we'll draw the same graph that's in the lecture here. So this is from the textbook though, so it's not really just from the lecture. this, 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 this. We'll number them. How do they number them? V1, V3, V2, V4, V5, V6, V7, V8. We define, we define a component. We'll say a subgraph of G is a component if it is maximal, I would say, and connected. Okay. So maximal is a little bit ambiguous, but we usually mean the same thing when we say maximal in this context. Connected, the definition of connected, right, is to say that, a graph is connected if for all x, y in the vertex set of G, there exists a walk from x to y. So this graph as a whole, just calling that G right there, right? If that's G, this is not connected because it's not true that from every between every pair of vertices there is a walk. So if I choose V2 and V5, there is no walk. That when I say a walk from x to y, I mean a walk where the first vertex is x and the last vertex is y. So there is no such walk, no such legal walk. I mean, you could say V2, V3, V5, but there's no edge from V3 to V5, so that would not be a legal walk. Now, the components are the maximally connected subgraphs. So subgraphs, first of all, I'm not going to put the definition exactly down because it's pretty intuitive. It's just the smaller part of the graph, right? So a subgraph could just be V5, V6. That's a subgraph. V5, V6 and the edge connecting them. Subgraph. It's a subgraph of this big graph here. Could also be V5, V6, V5, V6, and V8. And so then this edge would go away. Actually, I mean, all this would go away if I just chose that as my subgraph, but also notably that edge right there. But let's take, for example, this graph subgraph right here. This subgraph is connected, but it's not maximal in terms of what is, it's not a maximal connected subgraph. So that's I'm saying a lot of words there, but what I mean by that is like I can make this bigger and it's still connected. So I can make this subgraph bigger and it's still connected. I can still make this subgraph bigger and it's still connected, but I can't do it anymore. I could make the subgraph bigger, but it's not connected anymore. So we would say that this subgraph is a maximal connected subgraph. And so that is a component. Similarly here, take V2 to be a subgraph. Okay, it's connected because from every pair there's a walk. Okay, can I make it any bigger and it's still connected? Yeah, right. I can make it bigger, and it's still connected. Can I still do it? Well, yeah, I could make it bigger. Maybe imagine I make it bigger like that. Well, it's not connected anymore. Well, that's fine, but I could make it bigger in a way such that it is still connected. And if I try to make it any bigger, so I could include V4, or maybe I could include V8 or something like this, it's not connected anymore. So we would say that that is a maximal connected subgraph. So it is a component. And then finally, we have V4. It's connected. If I tried to include anything else in the subgraph, right, maybe that entire thing, whatever that is, it's not connected. So that's also a component. If I circle the right and middle, well, So it doesn't really mean like, okay, so someone's asking here, I'll take a screen. I'll copy this down. So someone's asking here if I just take a subgraph of what's on the right and what's in the middle, it's not connected, but is it maximal? Well, then you have to say maximal in terms of what, right? So I'm saying a maximal connected subgraph, which means it's as big as it can be such that it is still connected. So this wouldn't be, you're saying, it's not connected, but is it maximal? Well, it doesn't really make sense to say just is it maximal. It has to be maximal in terms of some parameter, in terms of something that we're talking about. So it's maximal in terms of connectivity. So this is maximal in terms of connectivity. This is maximal in terms of it's only allowed to have 5 nodes or something like that. Let's say there's some property that a graph can only have 5 nodes. Well, this is maximal because if you put it has up to 5 nodes. So if you put any more nodes, it'll have more than 5. But it has to be maximal in terms of some property. So this is maximally connected. This is not connected, and it might be maximal in terms of some other property, but it's not maximally connected because it's not connected. So I should really be saying maximally connected. So maybe I'll say that instead. Maximally connected. Hopefully that's clear. So that's the idea of components. So I know sometimes that terminology can be kind of weird, like maximal connected subgraph or maximally connected. So that's why I wanted to cover it here because I think it's good to draw these kind of do this little exercise, and it's just kind of good definitions to know. So I just kind of wanted to show that. So I don't really have a proof for this one. I don't really have anything to prove. I don't know. Can I think of something? Can I think of something to prove? I don't know. Unless the number of edges in a graph is the sum of the number of edges in each component. You could say that. That's necessarily true because there's no edges between the components, right? So I don't know. There's a theorem. It's a very easy theorem to prove because it's very true. But yeah. Okay, so I think now we can talk a little bit about another theorem, which is not the one that I just said, and where it's going to be talking about this. So for every tree on n greater than or equal 1 vertices, the number of edges is n minus 1. So hopefully that makes sense. Let's define a tree quickly. I want to just see what your guys' definition is. Connected and acyclic. So we say a graph. A graph T is a tree if it is directed and acyclic. So we can look at, I don't know, directed. What am I saying? Directed. Connected. Can have directed trees. That's what I'm thinking of. I'm thinking of directed trees. Connected and acyclic. So that is a tree. Acyclic, meaning has no cycles. Right? So if I connected that to that, there's a cycle. Right? This is also a tree. So we usually say it has some sort of branches and things like this, right? So this is a tree. Now, you can imagine maybe pinning this node in place, put a big X on it or something like that, putting a big pinning there, and then letting gravity fall, and we'd get maybe some graph that looks like, this. So you have 2 child nodes, and then you have this coming out the side, then you have this, so equivalent, right? This. That's the same graph, really. And now we'd say it's rooted. So we'd say rooted here. And you could have done that with any of the nodes. So you can root the tree anywhere. We're talking about rooted trees most of the time. Someone said, sorry, I missed the meaning of acyclic. It just means there is no cycle. So when I say, so there is no cycle. When I say that, I really mean, so first of all, we're talking about simple graph. So maybe a simple graph T is a tree if it is connected as acyclic. So we think about the cycles, right? We have like a cycle of length 4, a cycle of length 5, whatever. It's like a simple circuit, essentially. And we don't want that as a subgraph anywhere. So that's what it means for it to be acyclic, is that we don't have that as a subgraph anywhere in our tree. So we can root trees wherever we want to root trees and all that. So yeah, so we're essentially going to prove this, that for every tree, there's exactly one less than the number of nodes edges. And this is certainly true, right? So if I have a tree with, here's how many nodes we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And there's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 edges. And if I try to add another node, I mean, anywhere I do it, I'm going to be adding exactly one edge. If I were to add any more than one, what would happen? Let's say I added one more edge, I don't know, from here, and it connects down to there. What would happen now? Anybody have an idea? Why is this not allowed? We get a cycle, right? We have 1, 2, 3, 4, 5. So P5 or C5, I guess, right? It would be our cycle there. It's no good. So it's not a tree anymore. So as long as whenever we keep extending this tree, we're always adding precisely one new edge. And this starts at this kind of root position where we start with, I mean, that's a tree. It is connected and it is acyclic and it has 0 edges in one node. So now every tree can be created by just extending this one using this process of adding one node and one edge. You can't add one node. So the only thing you're allowed to do is add one node and an edge connecting that node to some other node. You're not allowed to add a node and connect it to 2 or more because it's going to make a cycle. You're also not allowed to add a node and connect it to nothing because then it wouldn't be connected anymore. So it wouldn't be a tree. So that's kind of a direct proof. I mean, I kind of, again, it's when we usually say things in words, we're kind of doing a direct proof. But let's look at the proof, using induction here, right? So we're going to use, induction. So the claim is that, every tree with n greater than or equal to 1 vertices has n minus 1 edges. So the base case is n equals 1. If you have only one vertex, then you necessarily are k1. And so then it is true that you have n vertices, n equals 1 vertices. And n minus 1 equals 1 minus 1 equals 0 edges. So hopefully that's pretty clear. And then now inductive, hypothesis. Suppose that, for all trees with n minus 1, they phrase it here as n minus 1. Yeah, let's say, with, let's say, n vertices, it has, or they have n minus 1 edges. So we'll see where this goes. So we'll have to modify this in a second, but we'll see why. Then show that for all trees with n plus 1 vertices, it must have n edges, right? So I think we can do this with regular induction. So I'm looking at the notes in the slides, and it's with strong induction, but we can't just do this with regular induction, because we know that any tree, yeah, I guess. Okay, I guess I do see actually why we technically need strong induction here, but I'll put a little fact, a little extra fact. I'm sure it's stated right after this or something like that, right? Yes, the next fact. So that's why they don't. Okay, so technically, to do regular induction, we need this theorem, which I'll just state right here, and we're not going to prove, but if graph G equals VE with at least 2 vertices is a tree, then it has at least 2 leaves. So a leaf is a vertex of degree 1. So it's just kind of hanging off the edge here. These are leaves here at the bottom. Those are leaves, right? That's also a leaf technically. Yeah, sorry, I should hold it there for a second. So that's an important fact. So that means that if I'm talking about a tree, and that tree has at least size 2, okay, then what we can do is we can talk about its leaves, that it will have at least 1 leaf. So that fact is needed now. Okay, so that fact is needed now. So without that fact, you can do this with strong induction. With that fact, we can do it with regular induction. So I'll maybe just for the sake of this, this tutorial, we'll do it slightly different than the slides. And so the point is that now we have a tree. Show that for all trees with n plus 1 vertices. Certainly, we have that we have 2 nodes at least, right? Because it's bigger than 1 and n is not 0. We never talk about n is greater than or equal to 1, right? So this is at least 2. So this counts. Like this counts with at least 2 vertices, that part, right? So that's fine. So we can take, so we're saying show that for all trees with n plus 1 vertices, they must have n edges. So we can take an arbitrary graph G, tree, I guess, arbitrary tree T with n plus 1 vertices. It must have at least 1, in fact it has 2, but it must contain at least 1 leaf node. So we know it actually has 2, at least 2 leaves, but we don't need 2 of them, we just need 1 of them. So it must have at least 1 leaf node. Call it, let's say X. So any tree that's at least size 2 will have at least 2 leaf nodes. So just pick some random one. Let's just pick that one, right? Let's say X is adjacent to a unique node y in G, in T. But we could maybe say through the edge xy. So right here, this step right there is where I used that. Okay. X is adjacent to a unique node y in T through an edge xy, right? So if I pick any leaf, call this x, it's adjacent to a unique node in the rest of the graph. Well, not the rest of the graph, in the graph itself, including itself, because there's no self loops, right? There'd be a cycle. So it's connected to a unique node in the graph. Call it y. Then what we're going to do is we're going to consider what's left over when we chop off x. Okay, we're going to consider what's left over when we chop off x. So this is going to be the graph t minus x. Okay, so we could now say, consider the graph t minus x, where we take t and remove x and the edge xy, because whenever you remove a vertex, you have to also remove all the edges adjacent to it, or incident with it, I guess is the word. We're not done, but just zooming out. So those are right. We're taking out that x, and now we know something about the graph t minus x. T minus x is in what is in that gray bubble here. We know something about it. And it's related to our inductive hypothesis, which is going to let us kind of conclude this proof here. Excuse me. Does anybody want to take a crack at it, like in the chat? What do we know about t minus x that will let us use our inductive hypothesis? I'm not asking the easiest question, but see if someone can piece it together. So I know there's kind of a lot going on, right? But we took this graph t, and I'm using this t as an example, right? But we know this works for arbitrary trees. We know that it'll always have some leaf. Okay, so we'll take one of the leaves. And remember, I started with this graph. It has n plus 1 vertices, right? So we take an arbitrary tree t with n plus 1 vertices. Then I chop off one of the leaves to get this graph t minus x. So what do I know about t minus x? And specifically, what will let me use the inductive hypothesis? Maybe another way, a roundabout way of answering the question is, when can I use my inductive hypothesis? What is the inductive hypothesis telling me about? Maybe that's an easier question, which is the same question as what I'm saying before. But what is my inductive hypothesis telling me about? Yeah, t minus x has n vertices. There we go. Right? There you go. Perfect. 2 people answered at the same time with the perfect correct answer. T minus x has n vertices. And that's what my inductive hypothesis is telling me, that for all trees with n vertices, they have n minus 1 edges. So that's great. So we know t minus x has n vertices. Since t had n, so t had, n plus 1 vertices. So t minus x has n minus 1 edges. I know that because of my inductive hypothesis. Any graph with n vertices has n minus 1 edges. There's a graph with n vertices, and so it has n minus 1 edges. And so t must have n minus 1 plus 1 edges, right? Which is just that one edge, the edge xy that we removed. So the edge xy that we removed. And it had to have been there. Like there's no way that, first of all, that we removed two edges, because there couldn't have been two edges from the leaf. Wouldn't be a leaf. Leaves have degree 1, right? Well, that pretty much answers it, actually, because we removed a leaf, and a leaf has degree 1. So it couldn't be degree 0, because it had to be connected. It had to be a tree. And it couldn't be anything bigger because, well, it's a leaf. So leaves have degree 1. So there's specifically one edge that was removed. And so we get that T must have n edges. And we're done. So there it is with regular induction. So there's the whole thing kind of on the screen here like that, right? So a lot of discrete math is induction, to be honest with you. A lot of graph theory is induction because of the way that graphs kind of work, right? We have that graphs are kind of build upon themselves, right? So it's a big, yeah. So, you know, the pigeonhole principle and induction are a big thing in graph theory. Okay, there's that question. If anybody wants a clarification of anything in this, please let me know. In the actual slides, you use strong induction, and that's because you haven't yet proved that every tree has at least 2 leaves. So it's not possible to say it must have one leaf node, call it X. We don't know that yet, right? So, but it's okay. You don't have to know that. You could just take any node, and an edge that it is adjacent to. So you take any node. It might be degree 1. It might be degree 2. It might be degree 3. It might be anything. I don't know, right? Take that node, and break it up and remove an edge there, and then you know how many edges are in the remaining ones, right? Because of strong induction, you know all the rest of them will have, you know, one less than the number of nodes, and then so the number of edges in the whole thing must be the sum of those two plus 1, and so you get the same result. But there must be some criteria for it to not break into many components. Yeah, it could. So the proof is there's a little actually a flaw in the proof in the slides a little bit. It might not make 2 components. Like if I remove this edge, this node and this edge right here, right? I shouldn't draw that, but if I remove this node and this edge right here, then I'm going to get 1, 2, 3 components. But that's fine. It still add up the sum of all the components there, but that wasn't mentioned in the slide for some reason. Someone asked me, could I go over it one more time? I'm happy to go over it one more time. So we're trying to prove, I guess I restated it here. Hopefully you can see when I zoom out like this. Zoom in a little bit more. I guess we don't need to see the box. Every tree with n, at least 1 vertices has n minus 1 edges. So the base case, pretty simple. A tree with only 1 vertex is that, has 0 edges. Inductive hypothesis. Suppose that for all n trees with n vertices, they have n minus 1 edges. Show that if we take a tree that's 1 bigger, it must have 1 more edge. So we take an arbitrary, we're trying to show that something for all trees with n plus 1 vertices. So we take an arbitrary tree with n plus 1 vertices. That's all I know about this tree. It has n plus 1 vertices. It's a tree and it has n plus 1 vertices. Then I do know that it has at least 1 leaf node. I actually know that it has 2, but I know that it has at least 1 because of this theorem right here. Okay, I'm getting a phone call, but I'm not going to answer it right now. Then we call that leaf node X. X is adjacent to a unique node Y in T through an edge XY. So there's our leaf. I've just picked a random leaf, whatever. It's adjacent to a single node in the rest of the graph. Well, whatever. Anyways, in the rest of the graph, let's just say, we call that Y, through an edge XY. Consider removing that node to get that, and the edge, the node and the edge, to get this graph T minus X. And T minus X is necessarily a graph on n vertices, and we know for sure that it must have n minus 1 edges. So, and we know that because of the inductive hypothesis. So we know that T must have one more edge because we created T minus X by removing a node and an edge. So if when we remove one edge, we get n minus 1 edges, then it must have n minus 1 plus 1 edges. So we have n edges. And okay, so that's that. When do I think the recording will be uploaded on YouTube? I'll do it right after this. So, we're almost out of time. I might just, we can maybe do one more question really quickly if we have time. Let's see. I can maybe squeeze in one more. I mean, of course, unless there's questions or something like that. These are not too hard. And maybe we can just, as a final thing, kind of get the chat involved. Show that the following pairs of graphs are not isomorphic by finding an isomorphic invariant that they do not share. So remember, graphs are squishy. You can move them around, but when you move them around, there's a couple things that don't change. The number of edges doesn't change. The number of vertices doesn't change. The degree sequence, like the specifically which nodes have which degrees, doesn't change. A bunch of things don't change, well, I guess I was gonna put this, but it's in the slides. Okay, I'll just put it quickly. So this is our list, right, of things that don't change. These are isomorphic invariants. So these are not isomorphic. Okay, this pair and this pair are not isomorphic. There's no way to squish one into the other. Why? So what? Try to see in the chat if you can figure out what is the thing that these two don't have in common from this list, and what is the thing that these two don't have in common from this list. And I'll leave that on the screen just for a minute before we answer it. Hopefully everybody understands the question, right? So I will answer it in a minute, but just give you guys a second. So there's something maybe about the number of nodes, maybe about the number of edges, or maybe any of those other things. So one person said number of edges are different, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. And here it's 1, 2, 3, 4, 5, 6, 7, 8. This has 8 edges, this has 9 edges. There's no way they're isomorphic. They can't be the same graph. And when I say isomorphic, it's a big fancy word, but remember, it's kind of just like squishing one graph into the other. When I showed that little simulation or whatever, like can you squish one graph into the other? Then they're isomorphic. And so there's no way, because how would you change the number of edges just by squishing it? I mean, that doesn't do anything. So correct, right? So this has 9 edges, and this has 8 edges. Okay, so not isomorphic. What about this? This one's a little bit more subtle. We have 5 nodes. They both have 5 nodes. Edges 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So they both have the same number of nodes. They both have the same number of edges. Okay. If it passes all of these, to be clear, that doesn't mean that they are isomorphic, right? So it's not sufficient, but it's necessary. Yeah, so it's the same person said one, and so someone else followed up. Then one vertex has degree 4, but the other one does not have that. Exactly. This has a degree 4. Degree V equals 4. And there is no vertex here that has degree 4. So, no nodes with degree 4. As you can see, the word node and vertex can kind of, you can use them interchangeably. So there are no nodes, there are no vertices with degree 4 in that graph, but there is one in the other one, so they cannot be isomorphic. Again, if I just squish one into the other, there's no way I'm changing the degree structure of it. Okay, guys, there's our very last mention of the day, right? That's our last thing. So yeah, it's 8 o'clock, so we'll wrap it up there. I really hope everybody enjoyed the tutorial and hopefully found something useful in what we talked about. We talked about a lot of different things. We went through some proofs. We got a little bit more familiar with different concepts in graph theory and all that. Yeah, hopefully everybody found it helpful. I will stick around for another minute while we finish up here, but that's all I'm going to cover. So if you have any questions, please feel free to ask me now, or you can always I don't know, leave a comment on the video or something like that. You can ask me after. But if there's no questions, then thank you everybody for joining. I hope you enjoyed. Good luck on the exam. It will be posted on my YouTube. Notes PDF will be in the description. Various other notes are available. Yeah, I don't have too much else to say. So yeah, thank you everybody.